Okay, so this is lecture 23, and getting towards the end here, we're going to talk about the Big Bang. So at the end, we're talking about the beginning. What I'm going to try to do here is talk a little bit about what the Big Bang theory is, and I think that idea is actually not particularly well defined, at least in a lot of people's minds. And once I talk a bit about what we mean by the words Big Bang theory, then I'm going to talk a bit about what evidence we have that this happened, that there was a period of time in the universe when things were very hot and very small. Okay. So let's just sort of back up here, as we've talked about a few times. In 1929, Edwin Hubble produced a landmark paper where he presented pretty convincing evidence that as you start looking at galaxies and measuring both their distances and their recessional velocities away from us, you see that there's a tight correlation between the distance to those galaxies and the speed of their recession. And this correlation is exactly what you would expect in a system that's broadly expanding, but more importantly, it's exactly what's predicted in the context of general relativity when you take a look at what's allowed for universes on the grandest scale. So this general behavior of an expanding universe was easily interpreted in the context of Einstein's general theory of relativity, and there were a number of physicists working at this time that had pointed this out. If we flash forward to today, we actually have an incredibly detailed picture of what we think the expansion history of the universe has been over time, whereas Edwin Hubble was looking very locally, meaning he was looking at galaxies that were within about 100 million light years from us and making this plot. We've now been able to measure distances and recessional velocities to galaxies that go out billions and billions of light years. And by looking at systems that are so far away that it takes light an appreciable fraction of the age of the universe to actually reach us, we can start to actually map out not only the fact that the universe is expanding now, but it was expanding in the past, and it was actually expanding at a different rate in the past than it's expanding now. And as I talked about last time, what was discovered sort of around the end of the last century is that within the last sort of few billion years, the universe has been doing something really weird. Whereas naively you would think that a universe made of mass that has stuff in it, if it starts off from some initial expansion, it's going to slow down because there's mass in the universe, and the mass in the universe wants to tug things back together. Naively, you would think, if you take a bunch of balls and you throw them up in the air, they're eventually going to start slowing down and maybe even come back down to Earth, right? And this is kind of what you would expect with an expanding universe full of galaxies, but this is not what's happening. What's happening instead is that in recent times, if you plotted, say, something like the size of the universe or a scale of the universe over time, then today what we're beginning to see is that the universe is starting to expand at an accelerated rate, which would be just like throwing some balls up off the air, and after they started to maybe fall a little bit, they would just take off in an accelerated fashion right off the Earth by themselves. This phenomenon associated with the accelerated expansion is called dark energy. And this is the evidence that we have for dark energy. The weird thing is, before that time, we see that there is a period where the universe looks like it's starting to slow down a little bit. And that's what you would expect in a universe that's dominated by mass. And so there seems to be a period of time in the earlier universe when its expansion history was dominated by matter, that matter has gravity and is kind of slowing it down in the expansion. But then right around today, or within sort of plus or minus a couple billion years, the universe is actually starting to accelerate in its expansion again. Why that's happening remains a mystery, but we have very concrete evidence that this is what's happening, because we can actually measure these things and see that this is what's happening. Putting that kind of stuff together, this evidence of a recent acceleration, together with other pieces of evidence associated with measuring masses of galaxies and galaxy clusters and how much mass there is in the large-scale universe, we've been able to put together this really surprising pie chart, which provides a census of what we think the universe consists of on the grandest scale. So you could, here I'm calling it composition of the cosmos. And we've all seen this before, but just to remind you, only 5% of the universe is in the form of normal stuff. okay, the kind of stuff that makes up you and me and stars and galaxies that we see. 25% of the universe is in something called dark matter. This is the stuff that provides extra mass, and you can think of it as the engine of galaxy formation. It provides the extra mass to make stuff want to collapse away from this original early expansion to allow galaxies to fall together and begin to form stars and stuff like that. And then there's this dark energy stuff, which is even weirder, which is driving the universe to expand at an accelerated rate today. So given this expansion history, this is sort of, it's very solid footing we have. We have a very, sort of, we're standing on solid footing that we have very strong evidence that the universe is expanding. Okay? And we even have pretty strong evidence that we know what the universe is made of, at least in a very broad brush sense. But the question is, just because we have all this evidence that the universe is expanding, does that really mean that there was a Big Bang? Okay? And what I mean by Big Bang, and I'll try to sort of define it a little bit here, is that there was a period of time when the universe was extremely small, okay? And if you push it to sort of the extreme of the mathematics, it was actually infinitely small, a single point, but I don't think anyone believes that that's actually what was going on at the very, very beginning. But there was a period of time when the universe was so very small that it had to be extremely hot. Okay, and so in just the same way that if you took a container full of air, okay, and you squeezed that container and made it smaller and smaller, that the air molecules inside that container would start bouncing across against the walls very rapidly, and that system would heat up. Okay, that kind of heating up, when you take something and compress it into a smaller region, is what we think had to have happened in the early universe if it was much smaller than it is today. So when people say the words Big Bang, or when a cosmologist says the words Big Bang, what they're really talking about is there was a period of time long ago, about 13.8 billion years ago, when the universe was so small, extremely compressed. It was very, very high density, very, very high temperature, so high density and so high temperature that no normal matter could really exist, that everything was broken up into a sea of elementary particles. And the question is, does this have to have happened? This sort of extrapolation to the very beginning, do we know for sure that that has happened? And I would say that just because we have overwhelming evidence that the universe is expanding today and has been expanding for billions of years, does that necessarily prove that this Big Bang epoch happened? Well, this idea of a Big Bang is so extraordinary. You know, Carl Sagan said that extraordinary claims require extraordinary evidence. And so if we're going to say something is bold and is, you know, bombastic, is that the universe began in this hot primordial state that was teeny tiny, we want to have more than just one piece of evidence. We want to have multiple pieces of evidence to hang our hat on. So let me talk again a bit more about the Big Bang Theory. So this is sort of a sketch, it's a cartoon about what the Big Bang Theory is. So the basic idea is, early on the universe was small and hot, and today the universe is very big and cold. And this period of time from hotness to coldness took about 14 billion years. And so when I say cold, I mean just a few degrees above absolute zero. So extremely cold. That's the temperature of empty space today. And when I say hot, I mean the equivalent temperature of empty space in the very, very beginning would be millions of degrees, if not higher, if not billions of degrees. So as you go back this way, it just gets hotter and hotter and hotter. And if you think you can extrapolate all the way to a singularity, then you're effectively talking about an infinite temperature. And we don't think that that's what happened, but that's sort of what we're talking about. So just to clarify, I'm not talking about the TV show, okay? Although the TV show makes my life a lot harder, because now when I try to find pictures of Big Bang, I always get their pictures. So here is a different sort of cartoon of the timeline history of the universe in the context of this Big Bang Theory. And I've put a few specific timelines here. And I'm going to come back to this figure again and again, so I'm not going to talk about each of the main epochs right now. But the broad history is something like this. In the very beginning, the universe was small and hot, and today it's cold. Now, the other thing I've done is I've sort of, we have this cartoon, and I've broken it up into a few epochs here. And notice that the timeline is sort of weird. It's not a linear timeline. So right now, as I'm focusing on the very early universe, you'll notice that I start, so the universe today is about 13.8 billion years old. The first line I've drawn here is 400,000 years. This corresponds to something like 400,000 years after the Big Bang, if we define 0 over here somewhere. And then today would be roughly 14 billion after the Big Bang. So I'm jumping a lot of time, and you'll see the scale is actually kind of oddly logarithmic. So I'm making huge jumps in time backwards. So while this is 400,000 years, this line here is only 3 minutes. And this line here is 10 to the minus 20 seconds. And here we are, 10 to the minus 35 seconds. And finally here at the very edge, that's something called the Planck time, and that's 10 to the minus 43 seconds. That period of time corresponds to sort of the earliest possible period that we can conceivably talk about within the framework of modern theoretical physics. We know that the models of theoretical physics break down at this time scale, because this is where gravity and quantum mechanics sort of come to a head, and we're not really sure what to do after this point. So this is sort of the absolute limit of times that we really can talk about with any sense of confidence here. So that's why this is written down. Okay. And the point is that as you go back into these earlier times, the nature of the universe itself changes. And broadly speaking, this is why. So I've done this before at the very beginning of the course, but I would just sort of want to walk through this again so we can sort of wrap our brains around it again. Let's imagine that we're all sitting in this room at this temperature, and then we start to turn the heat up. Okay, we start making it hotter and hotter in this room. What will begin to happen? So let's all leave the room so it doesn't get gruesome. We're going to keep turning it up. Okay. Eventually, if you start turning the heat up enough, all the water that might be sort of residually in the room will evaporate. Okay. If there's a puddle of water, it will evaporate out. And all the liquids will turn to steam. But eventually, if you start turning the heat up enough, even the solids will start to melt, right? At high enough temperatures, the solids will begin to either turn into liquids or just spontaneously turn into gases. And you'll eventually have a room that's filled with not complex sort of compounds and structures like this table, but if it gets hot enough, you can imagine the table melting and then eventually evaporating, and we just have a sea of molecules in this room. So it's just a sea of gaseous molecules that are bopping around, but we don't have anything other than that. And so suddenly all the complexity of the room, right? The room is pretty complex, like this table is solid and doing things, right? These chairs have folding mechanisms, all this stuff. Eventually, if you crank the temperature up enough, all that subtlety goes away. All that differentiation goes away, and we just have a gas of molecules, of different types of molecules and atoms bopping around. If you keep cranking the temperature up, then even those molecules won't be able to stay together, right? If you have H2O molecules and it's hot enough, and those H2O molecules slam together, you'll break the hydrogen and oxygen apart. And you'll just have sort of a gas of basically atoms. Now imagine cranking the temperature up even more, right? Then even those atoms will start to break apart. The first thing that'll happen is they'll knock the electrons off of each other, right? And then you'll have what's called a plasma. Okay, you'll just have nuclei and electrons and just sort of this crazy foggy gas of nucleons and electrons. At this point, if you were to peek into the room, you couldn't see through it. Okay, your light would not bounce from one side of the room to the other. Because as soon as those electrons are free, they'll block the path of any light that's trying to propagate through the room. So if you crank the temperature up that much, then what you have is this plasma, an ionized gas, and ionized gases are not see-through. It's a very foggy situation. All right? Let's crank the temperature up even more. Eventually what will happen is those protons and neutrons that make up the nuclei will break apart. That is, the nuclei themselves will break apart, and you'll just have a sea of neutrons, protons, and electrons. If you keep cranking the temperature up, even the neutrons and protons will break up into their constituent components. And all you'll have left is a sea of the most elementary particles imaginable. And so from this initially extremely complex state, right, where you have tables and chairs and all kinds of stuff going on, if it gets hot enough, then all that complexity must go away. And all you're left with is a sea of the most elementary particles possible, all doing basically the same thing. And we think that that's effectively what the universe was doing as you go back in time. As you go back in time, things are getting hotter, and therefore you're approaching this initial epoch of basically a primordial soup, an ultimate primordial soup that was nothing but primordial particles. So the universe, at some very early time, bestowed upon us a deck of cards, right? A few cards that represented all the primordial particles, the forces of nature, and then from those, what we understand now is 4 forces of nature and a handful of elementary particles. As the universe cooled down and expanded, all of the complexity that emerged came from that. In some sense, that's the ultimate quest of cosmology, is to understand how do we go from that very beginning to all this stuff we see around us today. So that's the story. What evidence do we have that something like this is actually going on? Well, what are the observational predictions of a model where the universe was very much smaller and hotter in the past? Well, as we talked about before, if the universe was smaller in the past, it had to be hotter. And one of the key pieces of evidence was developed actually in the 1940s and the 1950s, and eventually it really came to a head in the 1960s. That these theorists realized that if the universe was really that hot in the very beginning, then a glow left over from that initial kind of hot time, that hot period of time, should be observable today. And that should be observable as cosmic microwave background radiation. That is radiation that looks like a blackbody radiator that should be visible with a blackbody spectrum associated with something right around a few degrees Kelvin. So in fact, when we talk about what the temperature of empty space is today, being a few degrees above absolute zero, this is what we're talking about. We're talking about this residual glow from something left over from the Big Bang. Now, specifically, what we're talking about is a glow from the very early universe when its age was roughly 400,000 years. Prior to that time, it was so hot that all of the atoms were ionized. That is, it was so hot that atoms, atomic nuclei, could not hold on to their electrons for long before they got smacked by some other fast-moving particle and knocked their electrons off. So just like I said that if in this room we cranked the temperature up that it was enough that it was a plasma in this room, it would be foggy and you couldn't see in it. The same was true of the very early universe. When the universe was younger than about 400,000 years, it was a sea of free electrons and other stuff, and those free electrons kept light from propagating freely. So it was a very foggy place. You couldn't see. But after a point, about 400,000 years after the Big Bang, it cooled down enough that those nucleon, the core of atoms, the nuclei of atoms, could finally grab hold to freely passing electrons and hold on to them without being smacked by something else. The universe had expanded enough that the probability that it's going to get smacked by something else and lose that electron went to zero because it got big enough, low density enough, that suddenly the universe became basically neutral. When the universe became neutral, suddenly all that light that was bouncing around between electrons could start shining freely. And suddenly the universe became transparent. And that light today is what's visible in the cosmic microwave background. Now, at that very early time, the universe was hot. Okay? It turns out that the universe at that time was about 3,000 degrees above absolute zero. Almost as hot as the surface of the sun. The ambient space was almost as hot as the surface of the sun. The universe started letting its light fly freely, and what happened is that light just cooled down. The wavelength of those photons just stretched as the universe expanded. And so as you go from a time of a few 100,000 years after the Big Bang to today, you stretched from a black body spectrum that looked like a glowing hot pot or something like that to something that glowed in the microwave. Okay? So whereas a normal, like something we're more familiar with in terms of black body radiation might be at the surface of the Earth glowing at 300 degrees Kelvin, which glows in the infrared, or the surface of a red hot object glowing at something close to red hot. If you have something that's at a temperature of 3 degrees Kelvin, that has a black body spectrum that peaks in the microwave. And this is what a theorist named Robert Dicke realized and predicted in the 1960s. He said, hey, you know what? If I could just build a microwave telescope and go out and look, I should be able to see a black body curve of radiation coming from everywhere in space. And he set about doing that. So the idea is you have this period of time where the universe was not transparent to light. Suddenly it becomes transparent to light, and that light redshifts all the way to us. We could try to study it with radio telescopes. Unfortunately for Robert Dicke, about the same time he was doing these calculations, there was a really well-funded laboratory called Bell Labs, okay, which was almost like the Google of its day. Okay, it's where all the smartest engineers wanted to work. Okay, some of the greatest scientific discoveries ever were made at Bell Labs. Okay, they had basically a monopoly on the phone company, so they had a lot of money, and they put a lot of that money into basic research. And one of the things that a couple of the scientists there wanted to do is they wanted to build a radio telescope, and they wanted to use it to communicate with satellites. Okay, so they could build a better, signal receivers on Earth. So they built this thing, and they pointed it up in the sky, and they just pointed it at nothing to make sure their telescope was reading 0 the way it should, and they saw a black body spectrum. And they didn't know what to make of that, so they pointed in another part of the sky, and they saw the same black body spectrum over there. So they're thinking to themselves, boy, what have we done wrong with our telescope? Is there some source of microwaves around here that we don't know? So there's pigeon poop in the telescope, so they climb in there and they clean the pigeon poop out, and they're like, oh, maybe that was it. They do it again. They keep seeing this damn black body curve no matter where they point their telescope. So I said, let's call our friends over at Princeton who might know what's going on with that. I'm going to call Robert Dicke because he knows a lot. So he calls Dicke at Princeton, and he realizes when the guy tells him what he's seeing that, oh, we've been scooped. These people have discovered the thing we've long sought after. So these are the fellows that did it, Penzias and Wilson in 1965. They discovered this, and I'm sort of making light of it. I mean, they were serious scientists, and they did these, they built a very good receiver, and they knew what they were doing technically. And they eventually figured out that what they were seeing was this black body radiation left over from the Big Bang. And what they found is that space in every direction is 3 degrees above absolute 0. If you have an old TV with the old bunny ears, rabbit ears up there, not using cable, and you turn it to a station of static, some fraction of the static on your TV screen will be photons left over from the Big Bang in the microwave. You can actually detect some of those that way. These folks would receive the Nobel Prize in Physics in the late 1970s for this discovery. So what I've done here is I'm talking a bit about some of the big pieces of evidence that we think the Big Bang exists. And this one, when this was discovered in 1965, this suddenly changed the face of cosmology, right? Before that time, people thought, well, this is kind of weird, the universe is expanding. No one really knew what to make of it. Serious physicists were working on other things. They weren't that concerned about cosmology. But soon, right after this detection was made, people said, whoa. Maybe this whole idea that the universe has been expanding for billions of years and the initial period of time was very hot, maybe there's something to this, because we see evidence for it now all around us, exactly as predicted. And so the first two big pieces of evidence that convinced people that the Big Bang actually happened were the just observed expansion of the universe that we've been talking about, but also this cosmic microwave background, which was predicted to exist and is actually seen to exist. And this suggests that extrapolating the known expansion of the universe back to a point when the universe was about 400,000 years old, which is a long time ago, allows us to make predictions that are observed today, which suggests we know what's going on in a broad brush, all the way back to 400,000 years after the Big Bang. It suggests that the universe was about 3,000 degrees above absolute 0 at that time, and that it's 3 degrees today. Are there any questions about that? Okay. So let's move on then. There's a couple more things here that are brought. So what I've got here is the title of this is The 4 Pillars of the Big Bang. These are sort of what you could regard as the four really biggest pieces of evidence that the hot Big Bang actually happened. There's other pieces of evidence, but these are ones that are pretty straightforward to explain and are a pretty big deal in the context of the theory. So the next one I want to talk about is called Primordial Nucleosynthesis. And this has to do with the elements that were made at the very, very early time in the universe, when the universe was only a few minutes old. So here's this timeline that I've shown before, and as I'm emphasizing again, this period of time before 400,000 years is basically impossible to see, okay? If the only thing you have are light telescopes that see light, you cannot see this epoch because it was too foggy. When we study the cosmic microwave background today, and by the way, today, modern images of the cosmic microwave background are incredible. They're produced with incredibly high precision. They're effectively maps of the universe when it was just 400,000 years old. We can study that region of time in the universe's history with incredible precision. But before that time, it's like a wall. Light just is not propagating before that time. So if we want to test our ideas about what might have been going on at these very early times, we need to come up with another way. One way that's been very successful is this thing I've been mentioning called primordial nucleosynthesis. If theoretically you throw in all the modern physics that we know, and you assume the universe then continued to sort of shrink as you go back in time or continue to expand from some initial point, you could figure out that when it was only 100 seconds or so after the Big Bang, the universe should have been about 1 billion degrees, so extremely, extremely hot. And prior to that time, okay, if a neutron and a proton came close enough together to fuse into something new, it would just be broken apart again by the very speedy particles and energetic particles that were flying around in the universe. But after that time, the nuclei could start to clump together, okay? And in particular, eventually, as the universe cooled down and become low density enough, neutrons and protons came together to the point to create a really stable nucleus called helium-4, okay? 2 neutrons and 2 protons. And that was a very stable point. So in the very early universe, there was nothing but neutrons and protons, but eventually a good fraction of those neutrons and protons came together and formed helium-4 nuclei. And you can predict, based on what we understand about nuclear physics, exactly what the ratio of helium and hydrogen should have been that formed under these initial conditions. It turns out after that time, the universe expanded apart so quickly that nothing heavier than helium really formed. A little bit of lithium formed, but that was about it. The amazing thing is, if you go out into the universe today and you find basically gas clouds and very low, very unevolved stars, systems that basically reflect primordial regions in the universe, and you measure how much hydrogen and helium they have, the ratio of hydrogen to helium in these gas clouds is exactly what you predict they should be if we understand the conditions of the universe when it was 1 billion degrees. So this is sort of held up as a crowning success of the Big Bang model, because we can predict how much hydrogen and helium should have formed, very little lithium should have formed, very little beryllium should have formed, and nothing heavier than that. And you can go out and measure how much of these elements exist in gas clouds that haven't really been processed in stars, and what you find is that it's exactly what's predicted. So these 2 elements are made early, they're made with some ratio, and that looks exactly like what we see. Other questions about this? Okay. So let me just let's pause here and make sure we've all followed along. So why didn't the light elements form earlier than 3 minutes after the Big Bang? I said they formed at 3 minutes. Why didn't they form before that time? Good, it's too hot. Great. Wow. That was like the most enthusiastic response I think I've ever gotten in this course. So, great. Too hot, okay? Look for that on Friday in the exam. Kind of easy question to ask. Okay, I'm lazy, so there you go. Okay. And the fourth thing I want to talk about is, just broadly speaking, the observed evolution of the properties of galaxies as we look back in time. Okay? That is, we see the universe expanding today, but does anything else change as we look at things that are farther away, as if things were different in the past than they are now? Like, that's a very visceral thing that we can look for. Do we actually see it? And the answer is we see it. We see it pretty dramatically. So what's shown here is just some figures of galaxies, some pictures of some galaxies that were taken with the Hubble Space Telescope. The Hubble Space Telescope is great for taking pictures because it's up above the atmosphere, and so you have these very crisp images. So today, the universe has clear spiral galaxies and elliptical galaxies, and as you look back in time, say to just 2 billion years after the Big Bang, galaxies tend to be pretty ratty and messed up. Okay? And so while you have big extended spiral galaxies today, as you look back, things don't look the same. It looks like the universe has not really done its thing yet. This is just another picture. It's a little bit prettier picture. So this is an image. This is a local galaxy. Okay, and this also is a local galaxy nearby. But these things that are redder tend to be farther away. Their light is redshifted. So let's zoom in on a region here. And as you see, zooming in, look at that thing. That looks kind of messed up. And that's generally what you see, is that as you look at galaxies that are farther and farther away, therefore less evolved back towards the early universe, you see that galaxies are more messed up looking and kind of, are more like ratty looking, like that thing or these things here. This is just a plot that demonstrates this with time. So if this is today and this is 8 billion years ago, the blue line is how many big elliptical galaxies. Remember, elliptical galaxies are basically big balls of stars that are made mostly of old stars. And spiral galaxies are disks that are primarily made of young stars. And what you see that as you go out into the past, there's almost none of these old galaxies. It would be surprising, right? It would be sort of like looking at us and then looking at everyone in this room 20 years ago, or maybe that doesn't make any sense, 15 years ago, right? There'd only be one old person left, just me, and all you would be very young, right? Maybe there'd be a couple old people left, I'm not sure. So this makes sense, right? This makes sense that if you look today and then you go into the past, you don't see as many old things. Everything was still young, and only the things that happened to form very early are left. This is just a movie. It looks cool, so I would show it, just kind of making the same point. What's going to be shown here are different images that the Hubble Space Telescope has taken of nearby galaxies. All right? So this is a blow-up of a beautiful image of, this is again Andromeda, our nearest neighbor galaxy, and you can see it's very well formed. It's got a thin disk of stars. And so what we're going to see now is we're going to see lots and lots of galaxies as observed by Hubble in the local universe, and that's what these are. Okay? These big spiral galaxies and these chunks. And what we're going to do is we're going to fly through a zoom in on a specific region of the sky that Hubble has studied in great detail. And what you'll notice that as you fly deeper into space, we'll begin to see that the galaxies look more messed up. So while local galaxies tend to be fully formed and they have lots of spiral structure, etc., distant galaxies are more disheveled. And they also have higher star formation rates. Whereas if you look at any individual galaxy here in the past, it was pumping out a lot more light in newly formed stars than most galaxies do today, compared to average. So some of these young star-forming galaxies here. Now this is all done, a lot of this is sort of through the magic of computer animation. This is not really what things look like when they come off the telescope. But then what visualization experts who work with the Hubble data have constructed this to make it really look 3D as you fly through it. Like, look at this galaxy. It's all kind of messed up. It's got these 3 big regions that are forming stars, but it doesn't look like what most galaxies look like today. And as we go farther, we're going back in time. So this is a very early galaxy. These are becoming really, really early images of some of the old, 10 billion years ago, this system here. So the point is, as we look out, as we look deeper into the universe, we really do see what appears to be distinct changes in what galaxies were like in the past compared to what they're like now. Okay, so again, here are the 4 pillars of the Big Bang that we just talked about. So now what I want to do is now we're going to move into a little bit more speculation, but this is kind of fun because then we could start talking about, well, what about before that, right? Because there's this ultimate thing about getting closer to the beginning. What was going on as we approach the very, very earliest epochs, this sort of milliseconds, fractions of a millisecond for the Big Bang? The one thing I want to say, I want to preface this with is, up to about 3 minutes, we have an extremely solid understanding of what sort of had to have been happening, right? We've got Big Bang nucleosynthesis to hang our hat on. We've got really detailed studies of the cosmic microwave background. We've got, the evolution of galaxies up to this point. So we have a lot of sort of direct observational evidence to allow us to be very confident about what was going on up to this point. As we go from this point backward, it becomes a little bit more speculation. We have to rely on sort of what we've understood based on physics, based on studies of physics. Now, one of the things that's done that's actually kind of amazing, right, is because it was hotter at these early times and it's cooler today, if you want to know what was going on in the universe when it was very hot at these early times, you could try to do an experiment on Earth. You could try to create conditions that were very, very hot with very energetic particle collisions and see what you think should happen. And in fact, that's what's done in modern particle physics laboratories. So with giant particle accelerators, if you've ever heard of the Large Hadron Collider at CERN, it's this giant loop of particles that they get going around very fast, and they have another particle going around fast the other way, and they slam it together at incredibly high energies, which basically recreates conditions on Earth that haven't been recreated since the very early universe. Oh, yeah? Okay. Has anyone checked it?
Yeah.
Okay. Do we need to run out of the room, or are we okay?
No.
Okay. Good. Someone's lost. Okay. Hope they find the kid. Okay. So what are we going to do? So we can then. So what I'm telling you should have happened at these early times is based on our understanding of modern particle physics about what should happen at these higher energies. Okay. And we have a very good understanding of this because we can recreate at least up to a certain point higher temperatures in the laboratory on Earth. Now, of course, once we get past a high enough energy, we can't recreate those energies on Earth, and therefore it becomes really broad speculation. Okay. Okay. So let's go back to the very beginning. All right, as far back as we can conceivably push it. This is definitely to the point where it's wild speculation from the context of physics, but this is kind of also why it's fun. So this is at this time that's called the Planck time that I talked about before. This is 10 to the minus 43 seconds after the Big Bang. So extremely, extremely early. And what that really means is the temperature was extremely high. All right? At this point, we know this is the limit of modern theoretical physics because this is basically when general relativity and quantum mechanics have to come to a head. We have to reconcile the modern theories of quantum mechanics, the modern theory of general relativity for gravity, which right now do not play very well together. Those two theories are not united, but we know that at that energy, they're forced to unite. You start having quantum mechanical behavior of black holes and things like that that just, at some point you have to reconcile the theories. But if this is true, we expect that at this time period, at least there's sort of a hope in the context of theoretical particle physics, that all the laws of nature will be united at this energy scale. And I'll talk a bit about this, that we think now that as you crank up the energy scale of nature, that as you go from the temperatures today to these very, very, very early times, the forces of nature begin to unite. And we know, for example, that the electromagnetic theory and the theory of weak interactions actually does unite and becomes the same theory at these temperatures. And we believe that at a higher temperature, the strong interactions unite with the electroweak interactions, and you have basically one single theory. And so there's a belief that at this early time, you have some grand ultimate theory that might be delivered to us by string theory, where all the forces of nature are basically the same thing. And the reason why we see all the diversity that we see today is only because the universe has cooled down. As we step forward, we begin to get a little bit more confident in what might have happened. But again, we're still sort of in the era of speculation. We believe, in the modern context of modern theories of cosmology, is that at this time, when the universe was about 10 to the minus 35 seconds or so old, there was a really weird period in the universe when the universe was expanding faster than the speed of light. We think this had to happen in order to explain what's observed in the large-scale structure of the universe today. And also during this period of time, which is known as cosmic inflation, that's when all structure in the universe was seeded. Okay? So this period of inflation occurred very, very long ago. And a lot of people would say that during this period of inflation and before, that's not even really the Big Bang. That's like prior to the Big Bang. The universe is not behaving at all like we normally think of in the context of the standard Big Bang predictions. Sometime after that, let's say 10 to the minus 33 seconds, inflation is over. But around this period of time is when we think the strong, the weak, and the electromagnetic forces all became one united force. And then from that point, they separated to do different things. And again, while I'm on this side of this line, it's all still pretty speculative. We have no confirmation, experimental confirmation in the laboratory that this is exactly what was going on. But there are a lot of theoretical reasons to think this should have been going on, or perhaps what was going on. From a millionth of a second to 1 second after the Big Bang, this is when things are getting on a little bit more solid footing here. It was the first time when the universe was cool enough that neutrons and protons could even form. Okay, before that time, it was just free quarks. So today, in the context of modern particle physics, protons and neutrons are not fundamental particles. They're actually they're composite particles made of 3 quarks each. And these quarks like to live together in protons and neutrons, and it's really hard to pull them apart. But because it was so hot in the early universe, they were apart, and it was sort of like a weird sea of quarks. The other thing that was going on sort of around this time period is something called particle-antiparticle annihilation. And it was sort of like, you can think of it as the origin of matter itself. And so this is the last concept I'm going to talk about, and then I'm going to give a review. But this is kind of a fun concept to introduce, and it's something that's fundamental that we think actually was going on in the early universe. It's kind of amazing. Okay. So today we know, okay, this is not science fiction, we know that there are things called particles, and there are other things called antiparticles. Okay, antiparticles are a real thing. And in fact, antiparticles are created all the time in the upper atmosphere. It's known from direct experiment that if you take a light beam, a photon, and another light beam, another photon, and they're energetic enough, okay, they're both basically gamma rays, and you allow them to interact, they can create matter. Okay? They have enough energy, okay, to create E equals mc squared mass. Specifically, for example, you can create an electron and its antiparticle pair, something called a positron. Okay? An electron and a positron have exactly the same mass. It's just that one has a positive charge, the positron, and then the other one's the electron. The other one has negative charge. Okay? And we know this happens. So if you have energetic enough light, that light can come together and create electrons and positrons. You can create matter from pure energy. Okay, that's E equals mc squared. And so that's this direction. If you have 2 photons coming in, okay, they can interact and create an electron and a positron coming out. We know that happens. The other thing that we know that happens is if you put a positron in a room, it will immediately find an electron and annihilate and create 2 photons. There's not a lot of positrons in this room. If they were, it would be bad. Okay, it would spontaneously annihilate with the electrons and it would not be good. And gamma rays would fly out. We don't want that to happen. Okay? So there are not that many positrons around, but we can make them. And when we do make them, they interact very strongly with electrons and spit out light. Okay? The amazing thing is the laws of physics are symmetric in the sense that there's not an obvious reason why This isn't entirely true, but broadly speaking, you might naively think that there's no good reason why there are more electrons and positrons in the universe. But there clearly are. Okay? When Neil Armstrong stepped on the moon, it didn't suddenly annihilate him. Okay? The moon is not made of antimatter. Okay? It's made of matter. If it was made of antimatter, that would have been a bad first step, right? So we know that this is the case. And in the very early universe, we think both of these things were happening. It was so hot, the light was so energetic, that two photons would come together all the time and create electrons and anti-electrons. Okay, electrons and positrons. But then those electrons and positrons would just find each other again and re-annihilate into light. And so we think that basically this just kept happening. The universe was so dense and so hot that these things just kept switching back and forth. But as the universe expanded, the wavelength of all the light stretched, and therefore the energies of all the photons went down. And at some point, it shut this process down. If those two photons don't have enough energy so that they have E equals mc squared energy of a positron and electron mass, that is, if they don't have enough energy to create the mass of an electron and a positron, then they won't bounce in, they won't combine together to create matter. So that shuts that down. But any electrons and positrons that are around continue to annihilate. Okay? Just like that electron, if that positron found itself in this room, it would annihilate and spit out some gamma rays. So what happened is, as the universe cooled down, this process only went one direction. Okay? So I drew my arrow the wrong way. I realized this. Sorry about that. So this is annihilating, going to electrons, going to photons. So here's the crazy thing. If the universe had been symmetric in electrons and positrons, or in matter and antimatter, the only thing left after this epoch would be light, would be photons. There would be no electrons left. But instead, there were electrons left, and there were protons left. There was normal matter left. And so what we've realized is that there is this, built into the fabric of the universe is what's called the matter-antimatter asymmetry. For some reason, our universe was born with more matter than antimatter, and it didn't have to be that way. Okay? You can imagine it as a massive game of musical chairs, right? The chairs are the positrons, and the people playing musical chairs are the electrons. And when the music stops playing, you better be sitting in a chair, okay? And if you sit in a chair, you can imagine that's you annihilating. You're gone. And it's only the people who haven't found a chair that survive to sort of populate the universe. It's sort of a weird game of musical chairs, but anyway. It's like having 30 million people playing musical chairs, okay? And there being 30 million minus one chairs. That's what the matter-antimatter asymmetry in the universe is like. It's extremely, extremely tiny. But for some reason, there's just the slightest extra of matter over antimatter. And that matter that emerged from this original annihilation period is what allows all of us to exist. All the stars to exist, all the galaxies to exist, everybody to exist. The origin of this slight asymmetry in nature is sort of a grand problem that people don't know the answer to. But so I'm saying here, only 1 in about 30 million particles were left after this annihilation phase. Mostly it just produced light. Mostly it just produced photons. But a few particles were left over that basically made up all the sort of normal matter in the universe. Are there questions about this? It's kind of a crazy thing, but I thought it'd be fun to talk about. Yeah?
Does that correspond to the 5% of matter?
Yes. So the 5% of matter of normal matter in the universe is basically what's left over from this annihilation period. So I've talked about this before, but then once we get up to a few minutes after the Big Bang, that's the epoch when the first elements form. Okay? This is nucleosynthesis. And then after that is the epoch when atoms capture their electrons and light can flow freely, and this is what we see as the cosmic microwave background. Okay? So this is very well understood. This is pretty well understood. This is sort of understood. And then it stops being well understood after that. It becomes more theoretical as we push back. But that's sort of why it makes it fun, too. OK, so let me just finish here. I put this study guide up. OK, next class will be an overview sort of the course and sort of a review for the last exam. OK, thanks.